I can do this. Yay! Oh, that's awesome. Okay, that's what I want. I'm just trying something new out, y'all. Okay, I'll be able to use my iPad. I'm super excited. Okay, so we are time. Look, I'm a minute behind. So when you came in, you had exams in the front. Once you're finished looking at the exams, at any point you can get up and you can turn them back into the black basket over there. There's also Halloween candy. Happy Halloween. Be the last time I see you before Halloween. All right, so you will notice on your exam, if you look on the very last sheet, that's where it's graded basically. So you can see all of what the answer should have been, what you gave, and then how many points you got for it. And then it shows you your percentage score. You will notice that your percentage score is not what you see in Moodle. What do you notice? You had a 10-point curve. You had a 10-point curve. Okay. There had some people who got over 100% with that 10-point curve. So take a look, make sure you know what you did wrong. If you want me to look over questions with you, please let me know. I'm happy to do that. But it is a cumulative final exam. So please don't forget the material that was on that exam. Okay, questions? Okay, all right. So you need your eye clickers. You need your eye clickers. So, oh, and I owe you a joke, right? Okay, so why was it necessary for the meteor shower that made all the dinosaurs extinct? It was for the crater good. It's kind of a terrible one. For the crater good. All right, let's see. Oh, I think I have another one too that's better. Let's see. What did the aliens say to the garden? Take me to your weeder. Instead of your leader, take me to your weeder. Okay. All right, so eye clicker questions on carbohydrates, right? Everybody ready for this? Got your eye clickers out? You can do this. All right, select the correct match between the term and the description. Which one is correct? Remember, you have 1 minute. Five seconds. Make sure you click in. Okay, talk to your neighbors. What did you decide? On the chat, you're welcome to chat on Zoom. Remember, don't forget to check in a second time. Check in a second time. Calling it, supposed to be at 30, calling it in 5 seconds. So at 35, check in a second time. We had like 51 people. Okay. So what did we say? The correct answer? Good. Yay. If I could select it. How do we do on the first go around? Very good. Okay. So the correct description was that a disaccharide reacts with water to produce 2 monosaccharides, because di means 2, right? And it reacts with water. What kind of a reaction is that? Hydrolysis. Hydrolysis. Very good. Very good. Okay. What is the highlighted functional group? Identify the highlighted functional group. Please make sure those masks are over noses and mouths. Give you till 1 minute. Okay, 5 seconds. All right, go ahead and discuss and go again. 30 seconds. Don't forget on Zoom, you can chat. Okay, don't forget, check in again. Please go check in again. Okay. Grade 51, check in again. Trying to make sure y'all get all y'all points. Okay. So what did we say? Come back. All right. Oh, we were pretty divided, and then everybody kind of got on board. Okay, so this is an aldehyde. What did we say? Some people thought ketone. Why is it not a ketone? It's got to be how many R groups? 2, and there's only 1. So why is it not a carboxylic acid? What would it have to be a carboxylic acid? You'd have to have an O right there to be a carboxylic acid. Okay. All right, so last one. What is the highlighted functional group? It's going to be really difficult, I know. You got this. Oh, I can tell you all about homework too. Don't let me forget. Ten seconds. Ooh, we got 52 now. Okay, so talk around. Ooh, oh, what did I do? Here we go. Okay, discuss. Remember, 30 seconds. Ten seconds. Don't forget to check in a second time. We had 52. Everybody check in. Waiting for a few more, please, come on. I hate cutting it off. Okay, so what did we say? Okay, so we were kind of divided and then we changed. Okay, so we're between a ketone and a tertiary alcohol. So why do we think it's a tertiary alcohol? What do you have to have an alcohol? What do you have to have? OH. You have to have an OH. In the highlighted region, do we see any OHs? No. What if I selected this? And I said, what is this? I go to my carbon and I see how many R groups are attached to my carbon. This is an R group. This is an R group. So what is it? This would be a secondary alcohol. Okay. So make sure you can recognize those functional groups. That's a thing that you're going to need forever. Okay. No, we're not going to say the changes. All right. So I'm going to try something a little different. And while I'm trying something a little different, I want to remind y'all, so last night I had extended the homework chapter 5 to last night because we didn't finish chapter 5 until last time. But I don't know about y'all, but when I got home and the storm hit, I lost power and was out of power all night long into the morning. I was praying for a warm shower and I got it. But I don't know if that happened to anybody else. So if it did, I just wanted to I just wanted to make sure that everybody had the same opportunities. So I went ahead and extended it again through the weekend. Okay, so let's try this. I'm going to try this on my iPad just because drawing all these things is so much easier on my iPad than it is on this screen. So we're going to try it this way. We'll see how it goes. Okay, so I think we were not this far. Where were we? We were here, right? 6.14, is that right? Yes? Yeah, not head nodding. We did the first one. We did fructose, right? But we didn't do sorbose. Yes? Okay, so our instructions are to draw the Fischer projection for the enantiomer. What's an enantiomer? A perfect mirror image. So what are you going to do? You're going to draw everything that's exactly the same, right? So what's exactly the same? It's the stuff that isn't chiral, right? It doesn't matter. So you just draw that stuff. So my carbon double bond into an oxygen, that's achiral. So it doesn't really matter how you draw it. What matters is the stuff that's actually chiral. CH2OH. Okay, so now I'm going to add in my chiral carbons. So remember, everything that was on the left becomes what? Goes on the right. So I put a hydrogen here, I put an OH here, and I put an H here, right? And then everything that was on the right now goes on the left. And so we're going to put that as OH, H, OH. Yeah, familiar? Okay, so y'all have a definition of enantiomers, right? In your notes, we did that one last time. Yes, we did enantiomer. What else did we do? So your definitions, we did enantiomer, E-N-A-N-T. Enantiomer we did. What else did we do? Did we do isomer? Yes, no? No. Okay, so let's do isomer, because this is one you should know. What are the choices for an isomer? If this is D-sorbose, what is this one that we just drew? L-sorbose. The two are enantiomers of one another. This is the D isomer. This is the L isomer, right? Okay, so isomers can be D or L, right? If it's a D isomer, what do we know about it? How did I know that this is the L isomer of sorbose? I found the most distant chiral carbon from the carbon and participating in the double bond with the oxygen, and I look at the hydroxide, and I look at what side it's on. So we'll put that in words. The hydroxyl on the carbon farthest from the carbonyl carbon is on the what? Left or right? On the right. For D, it's right. So then we can do the whole thing, exactly the same thing for L, but what are we going to say? The OH on the carbon farthest from the carbonyl carbon is on the left. It's the only thing that's different. Yeah? Okay. All right. I'm going to give you two more definitions, so you kind of have them all together. So we talked about enantiomer being the mirror image, right? That means that all the chiral carbons, hydrogen and OH, are swapped, right? We agree with that? All of them are swapped. You're going to encounter molecules, sugars, where they're not all swapped, where only a few of them or only one of them are swapped. So let's talk about defining those, because you're going to have to know those terms as well. So we know enantiomer, we know isomer, epimer, E-P-I-M-E-R, epimer. An epimer is where one chiral carbon, the hydrogen and the hydroxyl, are swapped. And so we would call that like carbon 3 epimer, right? We would actually specify which carbon it got flip-flopped on. Sorry, that one's, the screen's not all the way down. Huh? How long they talk like that all day, right? Okay. So we have enantiomer is the perfect mirror image. Epimer is where you have only one, but there's something in between, right? You could have all or you could have one, but what if you just have a few? There's got to be a term for that. That's diastereomer. D-I-E-S-T-E-R-O-M-E-R, diastereomer. So this is more than one, but not all. Chiral carbons, hydrogen, hydroxide are swapped. So see how there are different possibilities depending on how many chiral carbons you have. So you ready to go identify a few more? We got this, right? We got this. Okay. So classify the structures A, B, and C in the figure as being either an enantiomer or a diastereomer of D-glucose. So look at D-glucose. D-glucose is D because we have the hydroxide on the right. Okay, so let's look at A. What's different? What I like to do is I like to circle the chiral carbon and the stuff attached to it that's different. So which carbon? Let's number them. 1, 2, 3, because y'all know I love doing that. 4, 5, 6. Which carbon is different? Okay, is carbon one different. It's not chiral, so we don't even, doesn't even matter. How about carbon 2? Same or different? Same. Carbon 3, same or different? This one's different. This one's different. I had the OH on the left, and now the OH is on the right. Okay, go down. Carbon 4, same or different? That one's different. Carbon 5, same or different? Same. Okay, so what do I have? Do I have an enantiomer or a diastereomer? Diastereomer. So A is a diastereomer. Is it an epimer? No, because epimer would be only one chiral carbon, but here we have two chiral carbons that are different. Okay, how about B? We don't care about carbon 1, so how about carbon 2? Is it the same or different? It's different. I'm comparing this one to this one. They're different. Y'all see that? Okay, how about carbon 3? Same or different? Different. Carbon 4, same or different? Carbon 5, same or different? Different. So what do I have? If they're all different, what do I have? This is an enantiomer. Remember that enantiomer is the mirror image. So if they're all swapped, by definition, it has to be an enantiomer. Okay, C. Which ones are different? So I got carbon 2's different, right? Carbon 3, same or different? Different. Carbon 4, same or different? Same. Carbon 5, same or different? Different. So this would be a diastereomer. So it's going to be really important for you to learn the definitions. Yes, but then you have to be able to apply the definitions. Okay, it's not just memorizing definitions. Okay, so now we're asked to draw the Fischer projection of the carbon 3 epimer of D-glucose. What's an epimer? We're only going to flip-flop one of the hydrogen hydroxyls on one of the chiral carbons. So what I'm going to actually do is I'm going to copy this. I'm going to try to copy this. This is why I love doing my iPad, because I can do exactly the same thing, right? So there I have exactly the same thing. What am I going to change? I got to find carbon number what? I got to find carbon number 3. So number your carbons. 1, 2, 3, 4, 5, 6, right? Carbon number 3 is right here. What I want to do is I want to flip-flop the hydrogen and the hydroxyl. So what I'm going to just do is go in and I'm going to erase what I have there, and I'm going to replace it, right? So now I'm going to have hydrogen on this side. I'm going to have hydroxyl on that side. So this is now no longer D-glucose. It's the carbon 3 epimer of D-glucose. Okay, but that was only part of it. Let's see if I can scooch it over again. Oh, you really don't like me, huh? Carbon 3. Oh, but it took my hydrogen. So weird. Why do you do that? Okay, so this is a hydrogen. This is a hydroxyl. Okay, now I want to do the same thing. But in B, I'm going to draw a Fischer projection of L-glucose. So what do I have to do to go from D-glucose to L-glucose? I need to what? I need to do a telling me to work. Come on. Copy. Where's paste? There we go. Oh. Okay. So what do? I want to go from D-glucose to L-glucose. I have to convert everything, right? Because can I just do the flip-flop? Can I just swap these two and make D-glucose? Will I have D-glucose? No. I'll have the carbon 5 epimer, and it will be in the D orientation, but it will not be D-glucose. It will be something completely different. So what do I need to do? I need to get rid of everything on this side, right? And I need to get rid of everything on this side. And then just go in and put the mirror image. So what goes on the left on carbon 2? OH, right? We're going to just flip-flop them. And H. See how carbon 2 is H and OH, and I swapped it to OH and H? Okay, what goes on carbon 2? H, OH. I'm sorry, that was carbon 3. This is 1, 2, 3, 4, 5, 6. See why I like to number my carbons? Okay, carbon 4. We get OH on this side, H on this side. Carbon 5. OH on this side, H on this side. Do we have an L isomer? Yeah, so this is L-glucose. So you see, you have to be able to go back and forth between the different things. Yes. Ask me again. These right here, it doesn't matter because they're not chiral. So it doesn't make a difference. So you're only looking to flip things that are chiral. If you put it, it would still be a correct answer if you put the hydrogen on the other side, but doesn't matter. Okay. All right. So the rest of this section, I'm sorry to say, is a little bit of memorization. So you have to learn about the different kinds of sugars. There's, I think 1, 2, 3, 4, 5, 6. There's like 6 different sugars that the book goes over, right? We got glucose. What do we all love to eat? Glucose. What form of glucose do we eat? D or L? Anybody know? We all consume D. Our enzymes know how to consume D. It's great. If you want to make a lot of money, you need to figure out how to make L-glucose in really high quantities for cheap. You want to know why? Our bodies can't metabolize L-glucose, but our taste buds can't tell the difference between L-glucose and D-glucose. So what does that mean? You could eat it, it would taste sweet, but you wouldn't get any calories from it because your body couldn't metabolize it. Right? Wouldn't you make some money? They can do it, they can make it, but just not in really high quantities for cheap. So that's kind of interesting. All right. So we're going to identify some of the different monosaccharides that match the description. So like if you want to make yourself flashcards for this kind of stuff, that would probably be a really good thing. So in combination with glucose produces the disaccharide lactose. Where do we find lactose? In milk, So lactose is actually a disaccharide. It's a disaccharide between glucose and galactose. Yes, and galactose. So we call that a glycosidic bond when we bond 2 monomers together. And that's what we're going to talk about in the next section, is actually how that works. All right, also called blood sugar. You could say D-galactose because basically everything's D. So what else do we call blood sugar? This is what we eat, right? It's the glucose. So it's D-glucose. Okay, also called levulose. Have y'all heard that before? Some people, sometimes. Levulose. So levulose is another name for fructose or D-fructose. F-R-U-I-T-O-S-E. If I could spell it, would be wonderful. But alas, you can't have it all. Okay. So then we talked about in the video, we talked about what happens when you have diabetes. And we've talked about this in class before, right? Yes, I think I remember that. So there are two types of insulin. There's type 1 and type 2. So one of them, usually you discover it in young people. So anybody know type 1 or type 2? Type 1. So this is type 1. And in type 1, right, there are two different ways that you can get diabetes. Number one is that you don't make insulin. And insulin is that signal, that hormone signal to your body that says, hey, I just ate, my blood sugar's high. You can take that sugar into the cells and use that to make ATP energy. So either you don't make the insulin, or the insulin that you do make, your cells don't respond to it. So it's just like it's not there. So type 1 is that you don't make it. So your insulin production is low. So how about B? Insulin often present, but glucose not transported into the cells. That's type 2, right? You're making the insulin, your cells just aren't responding to it. Can be managed with diet and exercise. That's type 2. That's type 2. Depending on what you eat and the more you exercise, the more responsive your cells become to the insulin that you are producing. So type 2 is much easier to control than type 1. So just make sure to go in and kind of review the different types of sugars from this section. Make yourself some flashcards, do something like that, because we didn't talk about all of them, but you need to know them. All right. So the next one is all about reactions of monosaccharides. And before I jump straight into the problems, I really want to, let's see, did I put myself some space? No. Okay, I need to put myself some space. I really want to draw some things out. I think it's really going to help y'all to understand, right? So let's draw glucose. Remember the stick diagram? What do we call that? We call that a Fischer diagram, right? So let's draw the Fischer diagram. And let's do something simple. Let's do this. And we're going to do straight chain. We'll do 1, 2, 3, 4 anomeric carbons, and then a CH2OH, right? And we'll put H, OH, H, H, OH, OH, H, OH. Okay. Draw this. Draw this. Draw this with me. You're with me, right? Okay. We have looked at sugars this way almost the whole chapter so far, but we've been lying to you a little bit. This is not how sugars are all the time. Most of the time they exist in a ring structure. And so you have this linear structure that gets converted into a ring. And so I'm going to explain to you how we convert from a straight chain, which is the Fischer diagram, into the ring diagram. So there are two really important things to look at. Number one, where is your carbonyl carbon? What carbon number is that? Carbon number 1, right? So put a little 1, 2, 3, 4, 5, 6, right? We've numbered our carbons. You have to know where your anomeric carbon is. Your anomeric, I haven't gotten there yet. Your carbonyl carbon, you have to know where your carbonyl carbon is. And remember when we were identifying if it was D or L, what will we look for? Your chiral carbon farthest from the carbonyl carbon. Which one is that? Carbon number 5. And we look at the alcohol and we say, is it on the left or the right? So what I want to do is I want to highlight those. And I want to say, okay, this one's going to be really important. And then my oxygen that's double bonded in my carbonyl carbon is going to be really important. Okay. So I'm going to zoom in on certain parts of the molecule, right? So if I have a carbon and it's double bonded, right? And I have, this is going to be a hydrogen too, because carbon needs 4. So that's a hydrogen too. So if you have a carbon that's in this kind of a orientation, right? And we have an oxygen sitting up here at the top. Tell me about the polarity of these bonds. And why did I put an extra oxygen? Oh, that's supposed to be my hydrogen. That's supposed to be my hydrogen. Hello. That's supposed to be my hydrogen. Okay. So tell me about the carbon-oxygen bond. Do they have the same electronegativity values? Carbon and oxygen, do you remember that? Go look in your best friend. They don't. They absolutely don't have the same values. Do you know which one's more electronegative? Look, which one's closer to fluorine than floozy? Oxygen. Oxygen is more electronegative. So what happens when you have a bond where one atom is more electronegative than the other? It's going to hog what? The electrons. That's what electronegativity is. That atoms want more electrons. So if you hog more electrons, what is your partial charge going to be? Partially negative. So remember how we identified things that were partially negative? We said you could do like this. And then the carbon would be what? Partially positive. Remember that? Yeah, sort of a little bit. Really important. Okay. Now, what actually happens with this stick is that it will fold in on itself to make the ring. So if I have one portion of the molecule that is polar, where I have other alcohol groups, I also have polarity. So if we kind of look at the ends, do you see how I've highlighted 2 different oxygens? One oxygen in the carbonyl, and then one on that last chiral carbon. So if we look at that last chiral carbon, right, we have that O, I'm going to put it in the same color, put it O here, right? And we have a OH, and then we have the rest of the molecule, right? And then you could put in your lone pairs if you like really loved your lone pairs, you know. But what's going to happen here is that you also have polarity. So I have another oxygen, and then my R group is really carbon, right? And I have that hydrogen up there. So what happens with the polarity here? Oxygen is, again, really, really electronegative. So what happens between oxygen and hydrogen like it does in water? Remember water, that superpolar substance? So the oxygen is very, what? Electronegative. Hydrogen is very electropositive. What do you see? I have a positive and a negative. Positive and negative are attracted to one another. So you're actually going to form a new bond. This is a new bond. But when you form that new bond, how many bonds does that carbon have now? 5. Is that okay? No, that's not okay. So we got to lose a bond. Where are we going to lose a bond? At the double bond. So I'm basically going to get rid of a double bond. But that oxygen is not happy anymore because it only has one bond. So what's going to happen? I'm now going to create a bond. Look, I have another partial positive and a partial negative, right? So I'm just going to create another new bond. And I'm going to lose this bond. Do y'all see that? All I'm doing is lining up positives and negatives. partial positives, partial negatives. So, okay, let's go back and look at our actual sugar. Where are these new bonds occurring? The new bonds are occurring between this oxygen right here is going to come up to carbon 1 and form a bond. That's going to be one of the new bonds that I drew. The other new bond is this hydrogen is now going to bond to this oxygen. And I know it looks far away, but it's not really far away because the molecule is folded over on itself. So if I redraw this in the now folded over method, let's see what it looks like. So I'm going to erase this stuff. What's going to happen? Let's draw the ring. How many things are going to participate in the ring? First of all, I'm going to have an oxygen, right? That oxygen is this oxygen right here. This oxygen bonded to what? What's the new bond? To carbon number 1. So what I'm going to do is I am going to make a ring that includes everything until I get back to the oxygen. So I've got an oxygen in the ring, carbon 1, then what? Carbon 2, then carbon 3, carbon 4, carbon 5. So that's actually 6 things because I have 5 carbons and my oxygen. Y'all agree with that? So that's 6 things in a ring. What does a ring that has 6 components look like? Does it look like the house? No, it looks like this number, right? Yeah. So your oxygen is this oxygen right here. It's bonded to carbon 1, 2, 3, 4, 5. Is that all the carbons in my sugar? No. How many more carbons do I have? 1 more. I can't use it in the ring because the oxygen's already there. So what do I have to do with it? I have to put it outside of the ring. So I'm going to put it up and I'm going to say that is CH2OH. So this is carbon number 6. Yeah? Maybe? Yes? Okay, good, 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 good. Okay, now, things are chiral, right? We have chiral carbons that are 2 through 5. So let's tackle our chiral carbons. How do I know where to put these hydroxyls and hydrogens? Everything that's in a ring in 3 dimensions, if this is the ring, can either go above the ring or it can go below the ring. So my question is, look at carbon 2, does the hydrogen go above the ring or below the ring? Well, there's an easy rule. If it's on the left, it goes on top. If it's on the right, where do you think it goes? On the bottom. Okay, so look at carbon 1. Not carbon 1. Carbon 1's not, we're gonna wait on carbon 1. Go to carbon 2. Let's do carbon 2. I want to do carbon 1 last. Our hydrogen, does it go up or down? It's on the left, so it's going to go up. So I'm going to erase my 2. I'm going to put H going up, and I'm going to put OH going down. But really, this is a skeletal diagram. So do I draw the hydrogens? No. So I can just put it as OH down, and that's just like saying OH down, H up, right? So because it's easier to look at, that's the way I'm going to do it from now on. Carbon 3, does my OH go up or down? It goes up. Okay, carbon 4, does it go up or down? It's on the right, so it goes down. Carbon 5's actually done because we have carbon 5 going to the oxygen, carbon 5 going to the oxygen, right? Then I have a hydrogen, but I don't have to show that one. And then I have carbon 5 going to my carbon 6, carbon 5 going to carbon 6. Do y'all see that? Carbon 5 is kind of done for you. So now my only thing that I have left is my carbon 1. How do I know for carbon 1 whether my new alcohol that I made goes up or down? You don't, because either way could happen. So we call it two different things. So let's put it up to start with. Let's go up. Do you remember when we were doing carbon-carbon double bonds? And we said if your R groups were both up, they were, what do we call that? Cis. If one was up, one was down, we call that trans. So we have a similar sort of nomenclature for this as well. So if the two things that you're looking at are carbon 6 over here, and it's not always going to be carbon number 6, but it's always going to be the last carbon that's outside of the ring. And you look at your OH on carbon, and it's not always going to be carbon 1, but it's going to be what's called the carbonyl carbon. So let's make our rule. So look at the last carbon outside of the ring. This will always be up. Always be up. That's by convention. We always draw it up. Then you're going to look at, and I have a new word for you. Look at the anomeric carbon. That's a new word, right? Anomeric. What does anomeric mean? Anomeric means this is the carbon that is participating in the new bond with the oxygen. So if you want to find an anomeric carbon, find the carbon that is bound to 2 oxygens. So I'm going to say this, carbon bound to 2 oxygens. So what carbon is my anomeric carbon? In my ring, what number? Bound to 2 oxygens. I'm going to highlight the oxygens for you. Here's one, here's the other. Which carbon is bound to both of those oxygens? Carbon number 1. Okay, so look at the anomeric carbon. If I could scroll up. Okay. If the hydroxyl attached to anomeric carbon is up, we call this, we don't call this cis anymore, but we're going to call this beta. But in the alphabet, what comes after B? C, right? That's how I remember them. They go together. B and C, they go together. So in the past, we've called it cis, but it's not really cis. In a ring, we call it beta. So if the OH attached to the anomeric carbon is up, that's cis. So they're both up, or both down would count as well, right? You could say that. Because if you turn the ring upside down, they'd both be down. Doesn't really matter. So our other possibility is if OH attached to the anomeric carbon is down, we used to call this trans, right? But now we call this alpha. This is alpha, which means one of them is up and one is down. So you have one up, one down. Okay, so what did we draw here? Look at my 2 highlighted things, my carbon 6 and my hydroxyl attached to the anomeric carbon. They are both up, so this is beta. What if I wanted to draw alpha? What would I do? Let's see, let me put in another page. So if this is my original, here's my original beta. I want to make it alpha. What do I do? And that's the symbol for alpha. So all I have to do is change, go to your anomeric carbon and change the hydroxyl, right? So now I'm going to make the OH go down. Now I have one above the ring, one below the ring, and I'm alpha. That's it. That's the only difference. Because when that ring forms, we don't know which one is going to happen. Either one could happen. That's kind of a gamble. But you have to be able to differentiate the two. Because once they're in a ring, they can't, those bonds can't twist. Okay, good. All right. I also did an extra tutorial video on that, and I posted that to Moodle. So it's in the chapter 6 material if you like need a refresher on that. So it's there. Okay. So now identify the following carbohydrates as the alpha or beta anomer. Now, isn't it so much easier to do this? Now that you know what it is. So what are we looking for? There are two things that you look for. We're going to find the carbon that is the greatest number, right? So in order to do that, you have to find your anomeric carbon first. So where's my anomeric carbon in A? Remember, bonded to two oxygens. Here are my two oxygens. Which one is my anomeric carbon? This one right here. This is my anomeric. If you have a carbon attached to the anomeric carbon, so if that H, instead of being H, were CH2OH, this C right here would be number 1, and this would be number 2. And then you have to go in the ring and number 3, 4, 5, 6, 7. But do I have a carbon attached? No. So how's my numbering going to go? It's going to be a little different. It's going to go 1, 2, 3, 4, 5, 6, right? So this was an aldehyde. What I drew before was a ketone. But it's the same numbering system, okay? So I found my anomeric carbon. I found my hydroxyl attached to my anomeric carbon, and I find my carbon with the biggest number. They are both what? They are both up, so we call that cis, which we now call beta. So A is beta. Okay, look at B. I'm going to find my anomeric carbon. So here's an oxygen, here's an oxygen. This is my anomeric carbon. If I have another carbon attached to it that's not in the ring, I have to give it the number 1. But do I have that? No. So I'm just going to name my anomeric carbon number 1, 2, 3, 4, 5, 6. Okay, so now I'm going to look at my hydroxide that's attached to my anomeric carbon and the greatest numbered carbon that's outside of the ring. What am I? I'm alpha because I have 1 up and I have 1 down. So I am alpha. Okay. All right, now you know all about the sugar that you ate in that candy over there, right? Okay, so the next thing that they talk about are reactions that occur with monosaccharides. This is from your book. This is just an image from your book. When you look at monosaccharides, right? We said you take 2 monosaccharides, you hook them together, and you make a disaccharide. How in the world do you hook them together? That's a great question, right? So what I'm going to do is I'm going to look at these 2 monosaccharides, right? Do you see the things in red? One is a OH and one is an H. what did we say happens when you take two monosaccharides and put them together? It's what kind of a reaction? A condensation reaction. Yay, a condensation reaction. You're going to make water. So in order to make water, I need a hydroxyl and a hydrogen. And that's exactly what's going to happen. I'm going to take away a hydroxyl from one of my monosaccharides. I'm going to take away a hydrogen from the other monosaccharide. And now what I'm left with, I'm going to take this oxygen and I'm going to hook it to that carbon. This is the anomeric carbon, right? So I'm going to hook this oxygen to the anomeric carbon. And when I do that, I now have what's called a glycosidic bond, right? So these reactions, if they go in the forward direction, that's the green, look at the green. If I have a monosaccharide and a monosaccharide, I make a disaccharide and H2O and water. So that's a condensation reaction. You make water and you join molecules, right? Okay. What happens if we go in reverse? What happens if we break that glycosidic bond? Now, instead of a condensation reaction, I have the opposite of condensation is hydrolysis, right? We have a hydrolysis. We use water, we break it, and we give part to part of the molecule and part to the other one. And so we go from a disaccharide and water to two monosaccharides, right? That's just the reverse of the same reaction I just showed you. Yeah? Okay, now let's go answer some questions about that. I think I put that below. Did I do that right? I guess that goes with the other one. We'll get there. We'll get there. We'll get there. All right, so this one says, draw the alpha and beta anomer of D-Altros in the Pyranose ring form. So like we called it a Fischer chain diagram, the ring we call the Pyranose form, but it's just a ring. So what's going to happen? Number your carbons. Number your carbons. Remember Dr. B's favorite thing to do? 3, 4, 5, 6. I've numbered my carbons. So what happens to make the ring? Over here, this hydroxyl farthest away, that's chiral, is going to come up and make a bond with that carbon. Right? Okay. So if that happens, this hydrogen is going to go and hook up with that oxygen. So put your oxygen first and draw yourself how many things are going to be in the ring. I'm going to have 5 carbons in the ring plus 1 oxygen, so that's going to be 6. So I need to draw myself a 6-membered ring. Then start numbering your carbons. Do you see how I don't have anything attached, any other carbons attached to my carbon in the carbonyl? So is this a ketone or an aldehyde? An aldehyde. So an aldehyde won't have a carbon coming down here, CH2OH, right? It won't have that. So you can always start an aldehyde as the anomeric carbon being carbon number 1. Okay, then go around 2, 3, 4, 5, and then 6 is not in the ring, CH2OH. Now I'm going to want to put things that are on the left where? Left goes up, right goes what? Down. Okay, so look at carbon number 2. Carbon number 2, OH is going to go up or down? Going to go up. Carbon number 3, down. Carbon number 4, down. Or you could do OH, you could do it this way, HO. doesn't matter. Okay, then carbon number 5, I've already got it bound to an oxygen. I've already got it bound to a CH2OH. So carbon 5 is good. Now I got to go back to carbon 1, right? What am I going to do? It depends, right? Let's do the alpha anomer. How would I do the alpha anomer? Alpha is 1 up, 1 down. So I'm going to go down. Right? Okay. So now I got to do exactly the same thing for beta, right? Everything is the same. But what's different? I change this to beta. What's going to be different? I find my anomeric carbon, which is carbon number 1 in this case. I take that hydroxide away and I put it going in the other orientation. So now they're both going up. Up and up is beta. Okay. All right. I did that in the video. Okay. Now, the next thing that we have to do is we have to talk about sugars and oxidation and reduction, right? So somebody remind me my oxidation reduction rules. What's my little mnemonic? I have oil, rig, right? So oxidation is loss of electrons. What else is it? Gain of oxygen, loss of hydrogen. And then reduction is the opposite. Reduction is gain of electrons, loss of oxygen, gain of hydrogen. Remember that? That's a good thing to just write on your paper. It really is. Okay. So now the sugar alcohol erythritol is often included in low calorie sweeteners. It's 70% as sweet as table sugar. Erythritol is the reduced form of the aldotetrose erythrose. Say that 3 times fast. Draw erythritol. So I need to take erythrose and I need to reduce it. Right? It's the reduced form. So what can I add to undergo reduction? Reduction is a gain of what 2 things? Either electrons or hydrogens. So in this case, we're going to add hydrogens. So let's add H2. Where can we put 2 hydrogens? Do you remember when we did this to our alkenes? What are alkenes? Carbon-carbon double bonds. And so we had hydrogens, and what did we do? We gave it to each of the carbons that participated in the carbon-carbon double bond. Do we have a carbon-carbon double bond here? No, but we do have a carbon-oxygen double bond. So what could we do? Give each of them a hydrogen. And so when we do that, we lose the double bond. So this O is going to become OH, right? Bonded to the carbon. The carbon had a hydrogen to start with, and we're going to give it a new hydrogen. So these are my new hydrogens that I've added to it. And then everything else is the same. Yeah. Can I simplify this portion right here? Can I simplify that? I could. How else could I write it? Your book does this. I could write that just the same as if I wrote, let's see, if I'll do it a little bit smaller here. CH2OH, and I got this. So how else could I write that? I got carbon bonded to what? 2 hydrogens, so I could call that CH2, and then that's bound to an OH. So either one is correct. Sometimes your book just jumps to that second one, and it's hard to see what's happened, right? Okay. All right, now this is what I was talking about condensation and hydrolysis. I just got ahead of myself. It happens. I get so excited. Just love chemistry so much. Okay. Identify the following reactions as either condensation or hydrolysis. So a disaccharide breaking into 2 monosaccharides. What's happening? Are you undergoing condensation or are you undergoing hydrolysis? This is hydrolysis. Very good. A reaction where 2 molecules combine, forming one, and a molecule of water is produced. Condensation. Okay, the breaking of a glycosidic bond. That's hydrolysis. Because a glycosidic bond is a bond that holds 2 individual monomers together. Okay. So now we have to analyze these glycosidic bonds. So name the glycosidic bond present. All right, so when we do this, you have to think about a couple of different things. So number one, we have to find our anomeric carbons. If we have 2 sugars hooked together, how many anomeric carbons are we going to have? 2. Okay, so let's number our carbons in the first ring. So I find my oxygen that's in the ring. The very next one, I go to it. If there's a carbon attached to it, I give it the 1. Is there a carbon attached to it? No. So I go ahead and give it a 1. All right. Then I'm going to go 2, 3, 4, 5, 6. Right. Now I want to do the next one. I find my oxygen, go down to the next one. That's 1 because there's no carbon attached to it. 2, 3, 4, 5, 6. To name a glycosidic bond, what you're going to do is you're going to name the numbers for the 2 carbons that participate in the glycosidic bond. So this right here is the glycosidic bond. Which 2 carbons participate? Give me their numbers. They are 1 and 6. That's how we draw it. 1 arrow 6. Now, how many of those 2 carbons are anomeric carbons? Only 1. Only 1. My anomeric carbon is right here and right here. Do you see how carbon 1 is anomeric, but carbon 6 is not anomeric? So then you have to name, is it a beta or is it an alpha orientation on that glycosidic, on that anomeric carbon participating in the glycosidic bond? So if you had 2 carbons participating, 2 anomeric carbons, you would have to say alpha alpha, alpha beta, beta beta, whatever it is. But because I only have 1, I'm only naming one of the orientations. So this carbon 1, are we beta or are we alpha? Remember, you're comparing to the carbon farthest away, and then look at the direction of that glycosidic bond. Is it going up or down? The glycosidic bond's going down. C6 is going up. So what do we call it? We call it alpha. I don't know which color I was. Alpha 1,6. So that's how we call it. Yeah? Ready to do some more? You got this. You totally have this. Okay, so the first thing we have to do for this one is to name the glycosidic bond and then draw the monomers that are produced. Okay, so I want to copy this first because I'm going to need that for later. Okay. All right, so let's look at this first. Let's name it. Find, number your carbons. So whenever I number my carbons, I find my oxygen. The next carbon that's attached gets a 1 unless there's a carbon outside the ring. Then that one gets a 1, but there's none. So that's 1, 2, 3, 4, 5, 6. Okay, number your other monosaccharide. Here's my oxygen in the ring. I go 1. Is that right? Why not? I have a carbon on the outside of the ring, so I can't number my anomeric carbon number 1. This is carbon number 1. My anomeric carbon becomes carbon number 2, number 3, 4, 5, 6. Did you see that? I've been warning you that that's going to happen. Okay, now, where are my anomeric carbons? Here I have an anomeric carbon, right, bonded to 2 oxygens. And then here I have an anomeric carbon that's bonded to 2 oxygens. Do you see that? How many different orientations am I going to name? 2, because I have 2 anomeric carbons participating in the glycosidic bond. Okay, name the numbers of the carbons that are participating. 1 and 2. It's an arrow. It's 1 arrow 2. We put them in parentheses. And then in front of that, we're going to write alpha and beta. So left to right or top to bottom, doesn't matter, but pick the first one, the first monosaccharide. So in that first monosaccharide at the top, alpha or beta? Up, down. So this is alpha, right? Up, down. This is alpha. Then look at the bottom. The bottom, we're going up and up. So that is beta. Yeah. Okay, so now we have to draw the monosaccharides that are produced from this thing happening. It's so easy. Find the glycosidic bond, right? Take away the oxygen. Take away that bond right there. See if I can erase it. Now, just in place of that, right? In place of the glycosidic bond, all you have to do is add hydroxyl groups. Done. How easy is that? Yes, something easy today. You needed it, right? That's it. That's all you have to do for the monomers. Wherever the glycosidic bond was, take away the glycosidic bond, give each one a hydroxyl. Okay. All right, let's do B. Name the glycosidic bond. You take a second. Write it down. Write your answer down. Take a second. Write your answer down. Okay, what did you get? Just call it out and then we'll go through it. You say the alpha, beta, and then you say the 2 numbers. Alpha or beta? Come on, be brave. Beta. Beta what? Beta 1, 4. Okay, so let's go and check. Let's go and check. So on that first monomer, find your oxygen within the ring, give the next carbon the number 1, unless there's another carbon there, and there isn't. So 1, 2, 3, 4, 5, 6. So 6. Okay. Let's do that for the other one. Here's the oxygen. I'm going to go 1, 2, 3, 4, 5, 6. I'm going to identify my anomeric carbons. How many anomeric carbons are participating in the glycosidic bond? Only 1. So I only have to find the orientation of the 1. So I have up and I have up or down. Up. So up and up is beta. And then I'm going to number them 1, carbon 1, carbon 4. Yeah? Okay. So now what I need to do, let me erase this stuff. Maybe erase would be nice. And we're going to have to draw the monomers, right? So how do we do that? Super simple, right? Whoop. Come over here. Oh, I cut off the bottom hydroxide. That's okay though. So what do? I erase my glycosidic bond, right? And what do I give each one? I give each one a hydroxyl. How do I know what orientation to go in? Whatever the glycosidic bond was. So if this one's going up, go up. If this one was going down, go down. Right? Not bad. Okay. All right. So these are, the next ones are just the similar sort of thing where you have to know your monosaccharides and know your disaccharides. So identify a disaccharide that fits each of the following descriptions. Ordinary table sugar. Like if you're going to go bake, you go to the store and you buy sugar. What kind of sugar are you buying? You're buying sucrose. You're buying sucrose. Milk. We talked about this one today. Lactose. Okay. Also called malt sugar. Maltose. Hydrolysis gives galactose and glucose. This is again lactose, right? So they asked the same question in the previous section, right? They just said lactose is a combination of glucose and what other monomer? Galactose, right? So not a big deal. All right. We only got a few questions left. One more question in that section, and then we got two more little sections to go. We are doing great. We are doing great. Y'all have a very happy Halloween. Make sure your exams are returned in the basket as you walk in the door. And let me know if you need anything. Have a great rest of your day. Anybody on Zoom need anything? Okay, I guess they're all going.